If you have heard anything about APX for FreeTOM, then probably you know about two characteristics of that system: poor performance and object-oriented nature. But is it possible to squeeze anything decent out of such a system? Hello, my name is Mark, and I continue my series about APX for FreeTOM. In the previous video I showed you the complexity of the hardware and its internal mechanics to support different high-level concepts in silicon: garbage collection, objects, capabilities, process scheduling, asynchronous ports, and so on. It wasn't a real test, but just minimal skeleton. In this video I am going to benchmark arithmetical performance of such overcomplicated processor. In the past there were a couple of good papers about APX for FreeTOM performance, but they were limited by existing tooling and lack of low-level programming. Let's try to dive deeper and see what we can achieve. First, we need to study the programming model of APX for FreeTOM. It has more than 200 different instructions. Most of them are arithmetical and logical operators, like divide to integers or compare two characters. But there are also high-level instructions that implement very complex operations. For instance, command to lock object or to send inter-process message. Data types are also quite extensive. There are different integer types, up to 32 bits, floating point numbers. APX was one of the first processors that anticipated the implementation of well-known IEEE 754 standard. And it also could be system objects and even objects of custom types. Stack exists, but it grows upwards, not downwards, in comparison to ARM or x86. And there is no direct push of pop instructions, but if instruction uses stack as source, it gets shrunk. And when destination operand points to variable in stack, it grows. Unfortunately, APX has no general purpose registers, and register file are the fastest memory in any processor. Only optimization that we can use is a 16-bit register called top of stack. Processor does not write value into stack memory right after operation, but keeps it in that register until next push operation occurs. One 16-bit register. Not that much. So if operand is not in stack and not in registers, it is in main memory. How addressing works then? The bad news is that it is complicated. Addressing is done in two steps. Firstly, GDP resolves address of a data segment and then it computes offset inside that data segment. Both parts has different encoding options, so let's start with data segment location. Let me remind you that one of blocks in code organization hierarchy is context. You can think of it as a function or procedure. Context can call other context. And variable resolution occurs inside context call. Each context has 4 sets of pointers to segments with variables. They are called entry axis segments. So to find a pointer for data segment with referenced variable, the GDP needs to select an entry axis segment, one of 4, and then find relevant record inside them. First mode for segment selector encoding is direct mode. Immediate value encodes 2 bits to choose entry segment and 4 or 14 bits to choose an axis descriptor for target data segment. Another similar mode is to use the top of the stack instead of immediate value from encoded instruction. And more complex way to reference a variable is indirect mode. It is two-stage resolution. By using object selector with direct addressing, GDP finds first data segment. And then it reads another direct object selector from that data segment to finally locate data segment that contains target variable. Okay, now we know what data segment has our variable. But segments can contain multiple records. It would be too expensive to have one segment per variable. So we need to find a record inside segment. That's why GDP also requires offset to be encoded inside instruction, and again it is quite flexible. In basic case it is just an immediate offset, but it also could be computed value with free variations. If we want to access property of an object, access a static array element with known fixed base, or access to an array element by dynamic base and dynamic index. To simplify, we can say that final offset is just a sum of two values. Each of them could be either immediate value, top of stack register, another variable from the same segment, or from another data segment. It is important to mention all that internal stuff to have understanding about relative performance of different addressing modes. Let's say if you want to use indirect addressing for segment, then it would be very slow because of a few extra memory accesses while you don't have segment registers or other ways to optimize it. So, as you can see, architecture is quite standard. Nothing too unusual. Just a lack of registers and complex addressing modes. So let's try to write some code and see what we can achieve. As usual, first program would be hello world. But before that we need to understand how to output something to console. To interact with outer world, APX for FreeTOM can use inter-processor communication and interconnect memory space. IPC is quite complex and requires setup of communications channels. But interconnect memory space is much simpler. Because we implement memory bus slave in FPGA, we can use it to monitor accesses to that space and output data via UART to PC. From APX for FreeTOM side, it should be special interconnect segment, which declares what physical addresses would be used for GDP access. And that's it. By using special instructions, move to interconnect and move from interconnect, processor can read and write data to that space. Of course, I had to write simple compiler to avoid complex encoding of instructions by hand, so all listings are in some kind of assembly that resembles a higher level language because of APX nature. All my programs have just a single context and a single data segment for variables, so object selector is always the same and we can use direct addressing for all variables. So let's see how hello world for APX for FreeTOM looks like. There are two sections with compiler directives to declare stack and variable segments. We have message to send, its length in words, and auxiliary variables to interact with interconnect register that are reserved for UART transfers. Two interesting details. You can notice how I reference current word to output by using pseudo variable data, which means that base part of address is 0 and only index is used to compute final offset. It allows to save few bits in instruction encoding. And also, unfortunately, we have no conditional branching except boolean check. So at first we need to set boolean variable with result of comparison operation and then use it to branch. Other than that, it's quite straightforward code. We just send characters in pairs until we reach end of the string. And we can see that it works. Even if premature optimization is the root of all evil, we still can do some optimizations to make our code faster. At first we want to minimize the number of memory accesses, so we can use stack operations to avoid extra memory accesses because top of the stack is the only processor register that we have access to. As I already mentioned, we are going to use direct segment addressing for all variables and APX has some kind of caching layer, so it should help here as well. Direct addressing has two forms, long and short. In long form we have more bits for offset or index, but actually there is no difference in long-short direct addressing. But because shorter instructions require fewer memory fetches for the code, then it should be faster. So we try to optimize length of instructions bitstream and we are going to use shorter form of direct addressing where it's possible. Also, I noticed interesting behavior. 1 byte variable comparison is 6 ticks slower than 2 byte comparison. It's not related to memory. Log shows same amount of requests, so it should be caused by arithmetical logical unit block itself. I don't know why, but it's not a big deal. Another detail that I had to take into account is scheduling policy of processor. If process runs for a while, GDP puts it into scheduling port. I fixed it by changing frequency of external tick source from 1 kHz to 0.1 Hz, 1 tick per 10 seconds. So we had plenty of time to execute our program. To evaluate performance of APX for FreeTool, I am going to use my favorite benchmark, computing pi number. It is quite simple and I already have some numbers for other processors. I chose Spigot algorithm because it is trivial to implement and has no floating point operations. It is just integer arithmetic and comparison. I am not going to explain it in details, but you can find a bit more information in my previous videos about pi computation. The code is more or less straightforward, but of course there are few specific details related to APX architecture that I want to mention. Even if APX for FreeTool is object-oriented processor, there are no type checks for scalar values. Variables in memory could be used in arithmetic operations regardless of their type. Scalar values even could be treated as arrays. It doesn't matter much in that program because we are not that limited in memory, but it's still interesting. I have found only one way to pop value from stack without extra access to memory, by using conditional jump operation. This operation is not on hot pass, but it's still nice to have. Division is split in two instructions, to compute the quotient and remainder. It's not like for modern architectures when a single instruction returns both values. Other parts should not cause any problems with understanding. We just compute digits and output them. Okay, now it's time to see results. I got such numbers for different amount of pi digits. For 2048 digits, APX for FreeTool beat all my previous calculations. For 8192 digits, it took about 8 hours to compute, and it's much faster than more advanced Chudnovsky algorithm on Intel 8080. But how it compared to Intel's processor of the same era, groundbreaking 8086? My real 86 machine is not working right now, so I had to use simulation, and on tick accurate 86 box, same Spigot algorithm was 2.5 times slower. Surprise, surprise! I always read that performance of APX for FreeTool was poor, but now I see that it's not that bad. How is this possible? As usual, answer is not that simple. First, I doubt that a lot of people wrote assembly code for APX for FreeTool, and other compiler from Intel was famous for their poor optimization techniques. It was used for writing object-oriented code, not to be computationally efficient. Objects were main concept for APX systems, so no blame about that. Another argument is bit width. APX natively supports 16 bits, 32 bits and even floating point data types. But 8086 is much slower for 16 and 32-bit operations. Maybe also platform itself matters. I used FPGA implementation of memory controller with zero weight states for memory operations. But as far as I can tell, emulated system in 86 box has a similar memory latency. So it is not main reason. I am very pleased by results of hand-written code and got exciting journey to run such complex system as APX for FreeTool. Hope that you enjoyed it as well. See you in next video. Bye.